keep your eye on the page, prize, and polymerize. So this morning I need to run 5 SDS page gels, and so I am currently casting or pouring 8 of these. And so we make our own because we go through so many. This is going to be like up to 782, I think. I keep track because I number them so I can cross-reference. But so what am I talking about? So PAGE, polyacrylamide gel electrophoresis, is a way that we can separate molecules, like proteins and RNA molecules, separate little bits of them to look at and see if various things are there, using a gel made out of polyacrylamide and using electricity, which is the E part in the page, to send those molecules traveling through the gel towards a positive charge, because we make them negatively charged, or they're already negatively charged, and then we move them through the gel. So a common one is SDS page, which we use for proteins, and so we denature or unfold the proteins, coat them in this negatively charged detergent called SDS, and send them traveling through the gel, and they're going to separate based on their size, because the longer ones are going to get tangled up more in this gel mesh that we make out of polyacrylamide. There are also other types of page gels, so you can do like a native page where you don't use the SDS. So you're separating based on shape instead of the like unfolded length of the proteins, and that keeps complexes together as well. And we can do things like a urea page to separate RNA. And so today I want to tell you more about how we actually make these gels, because it's really cool, because we're actually like doing the polymerizing. So if you run like an agarose gel, so separate DNA pieces, those are like a thicker ones, they're in a slab, they're in a horizontal slab, as opposed to these thin vertical ones. When you do those, then basically the agarose is already these long chains of sugar. So all we do is we take this agarose powder, the sugar powder, and we make a solution of it, and we heat it up and dissolve it, and then it kind of like knits itself into a mesh. But with the polyacrylamide, we have these acrylamide monomers, so there's individual units, and then we get to polymerize to like link up together. And we have like they make straight chains, and then we have these ones that do cross-linking, and so they like link up different chains, so you get this mesh. And you can add different amounts of the cross-linker and of the non-cross-linker one, and you can add like different percentages. You can make a high percentage gel if you want to separate really small proteins, so you make the mesh really tight. You can use a lower percentage if you want to separate big proteins, so make a looser mesh. And we also have like a running gel, which has which is where we're going to do the resolving, so separating things, and then a stacking gel, which is a looser mesh on top to get all the proteins to the start line at the same time. With like an RNA urea page gel, we don't have that, so you have to be careful when you're doing the pipetting, and so I'll talk more about this various stuff. But this polyacrylamide electrophoresis is really useful, and being able to cast your own gels is really useful. So you can buy pre-made gels, and so we do that with some of our like gradient gels if we want a gradient to separate proteins from a range of sizes. But when you go through a lot of them, it makes a lot of sense to make your own, especially if you want to customize the various percentages and that sort of thing. In addition to customizing the percentages that we use and the concentrations of cross-linker, non-cross-linker, that sort of thing, we can use different thicknesses and different numbers of combs. And when you make your own, you feel a lot less guilty when you're just running like a single sample in a gel, as opposed to like wasting a whole one of those pre-made ones. So the pre-made ones come in these like plastic casings that you like crack open. We have these glass plates, and then we pour the liquid into the plates, and so I will show you how it's all done. So today's post is going to be, part of it is going to be from a post I made last year that I've refreshed and added some new figures to, fixed a couple typos, that sort of thing. But I really am making a bunch of page gels this morning, and hopefully I don't have too many leaks. There's one that's leaking, but the rest look okay so far. Okay, so let's talk about how this is all going down. So I'll talk about how we do it, then I'll show you how we do it, and then I'll talk about what's actually going on. So we have like master mixes that we make, which have like buffer and so like a pH stabilizing agent, and then acrylamide solution. And so you can use different amounts to get like a higher percentage for separating smaller things or a lower percentage for separating bigger things. And don't worry, I'll go into all this more in detail. I just wanted to give you like a look at what it looks like first. And so on its own, these are, so we have like a running gel and a stacking gel, because for SDS page typically, so what we do is you do like a running gel, which is where you're actually going to have the separating. So sometimes this is called like a resolving gel. So this has a tighter mesh, and typically I fill it to like this green line. And then on top of that, you have your stacking gel, and that has it's a bigger mesh. So bigger holes, and basically this allows everything to get to the start site at the same time. So basically, once they get to that tighter mesh, they're gonna get slowed down more, but they can all like anything of any size can kind of travel easily through the stacking gel. And this allows like all the molecules to get a head start, because you're gonna have these lanes. So we put in a comb, well, before the stacking gel sets. And so now this is, when you take this out, you're gonna have wells, and that's where you're gonna stick things in. And so you do the stacking gel so that things can, even if you like pipetted it so that that molecule was right on top where you pipetted it, it'll get to start at the same time as the thing you pipetted first. So that's the point of the stacking gel. And so for some types of gels you don't use that, like for urea page we don't do a stacking gel. But then you have to be really careful that you pipette only at the very bottom really carefully, and don't like, yeah. But anyway, so when you make this, when you pour in the stuff, so basically you can just pipette it from like the corner slowly, or else it'll like overflow. You don't want it. And so, but basically at this point, like this is all liquidy. It's liquidy. It's not gonna polymerize on its own. We have to make it polymerize, and how we do that is we use an oxidizing agent. So we use like a solution of APS, ammonium persulfate, and then in the hood we have TEMED, T-E-M-E-D. And what these are going to do, yeah, we use it in the hood because it like smells really, really, really bad. So yeah, so we do that part in the hood. But you don't want to add that until like right before you're ready to pour the gel, because once you add that, it's going to start this chain reaction. And this chain reaction is a radical reaction. Like, by radical, I don't just mean like it's amazing. It is amazing, but it means that there's like a lone electron. So molecules atoms link together to form molecules by sharing pairs of electrons. They really don't like having a single electron. This is like super duper unstable, because electrons love to be in pairs. So sometimes you have like a lone pair of electrons, like on an oxygen or a nitrogen, they have like a pair of electrons. That's all cool. But having a lone electron, that's a no-no. So we call those molecules radicals, and they start off chain reactions because they're going to try to steal an electron from something else. And so they go and they steal an electron from something, and then that thing is missing an electron and has a lone electron, so it's a radical. So it attacks something else, and you get these chain reactions. And when this is happening, when it's attacking these acrylamide, you get these chains. And it also has like, so it's acrylamide bis solution, and so it has like 29.1, so this is just a different thing, but so it has like bisacrylamide, this and so it has things that'll form cross links between the different chains. And so by varying the percentage of that too is another way that you can change the amount of mesh. So you can imagine if you have more cross links, you might have a tighter mesh. But basically, so you make these long chains and these cross links, and so sometimes the radicals will like terminate, and so they'll bind to something else that has a free radical, and then they make a pair and everything's good. But for most of the time, what they're doing is this chain reaction where they're going from one thing to another. So it happens really quickly. And so you want to make sure that you have everything set up. Like you even have like, I put my pipette tips, get them ready so I can add the APS. Then slowly invert it, you don't want to get bubbles. Then go add the TEMED, slowly invert it so you don't get bubbles, and then bam, it's in here. And so what I do with an SDS page gel is I fill it to about this line, And then what I do is I have this ready to go too. So I keep like a pipette, like a big 1 ml pipette, with like a ml of isopropanol. And I just make a layer on top. And so basically the isopropanol, it's not soluble with the other mixture. So it's going to form a layer on top, but it's gonna both keep the top from drying out and help you get like a nice clean line. So you can kind of wiggle it a little. You wanna make sure though, so then you leave that while this part's drying. And so typically to see that when it's dry, what I do is I keep the excess. So I make the mix in like a falcon tube, and then I keep the excess in here, and I keep the pipette in the pipette tip in here. And then when it's hardened, you can tell because the pipette tip will get stuck in the gel, and it's fun because then you can kind of like play with it. But anyway, so that then you know it's done. You can then pour off the isopropanol, do like a water wash. So it's helpful if you have like a squirt bottle. You can do like a water wash, pour it off, and then I should really try to dry it out. Just like put a paper towel or whatever, and it'll like suction out. And then you can add your stacking gel, and when you add your stacking gel, you want to have your combs ready. So we have different size combs. So we have like different numbers of wells. So we have like 15 wells and 10 wells, then we have 0.75 and 1.5. So we have these two thicknesses of plates, so 0.75 and 1.5. And what the thickness difference is in the glass spacer. So the 1.5, this one, is going to have a thicker slab of gel than the 0.75. So you can use either depending on how much sample you have, how much you want to load, and all of the various things like that. And so then when you add the glass on top, you get that hole, and that's where the gel is going to be. So if you have a 0.75, it's going to be thinner. For other types of gel, so like when we do urea page, when we do like the bigger ones and stuff, you actually have to put your own spacers in. And so you just have like 2 plates, and then you can put different width spacers, and then clamp them together or tape them together depending on the gel in the system. But for these gel systems, so we have this caster, like, so we have the plates, and then we have these casters. The important thing is you want to prevent leaking, and so we have these, or those, I don't know what you call it, maybe those are clamps, I don't know, but then you have these casting welt tray things, and they have this rubber part on the bottom. So what you want to do is you want to put the short plate in front, and then these, they have this like hole, so you put it down through here. Sorry, it's hard to do this while filming. Okay. And then you clamp it down. What you want to do is go to the bottom and run your thumbs over the bottom and make sure it's even. If these plates are not even, you're probably going to leak. Even if the plates are even, you still might leak. So basically this goes down, and then this clamps on top. Sometimes these can come loose, and what can be helpful is if you actually stick like a pipette, like a P1000 tip in here. This can prevent leaking. So if you're starting out and stuff, it's often good to try just putting water in and seeing if the water leaks, and then you can pour the water out and cast your gel. So typically it takes probably somewhere between half an hour and an hour for each of the different sets to polymerize. And so you do the same type of thing for the stacking and the resolving gel. In terms of like, you add the polymerizing reagents right before you do the reaction. Or else it'll harden like while you're preparing or whatever. And you want to make sure that like you add the 2 reagents, so the APS and the TMed, you want to like add them quickly after one another, but after a little shaking, so you don't get like pockets of that are polymerized and others that aren't. So you want to make sure it's mixed, but you don't want to introduce bubbles while mixing. So just like invert up and down a few times typically does the trick. For some type of gels, you really need to avoid bubbles. Like if you're doing sequencing gels, like urea gels, like those really big ones that are really thin. So in those cases, you can like degas it, where you have basically like this like filter device, and then you're just kind of like spinning it and getting out any bubbles. But other than that, another thing, so make the APS, it's good to make it fresh. Keep that in the fridge. A lot of places say like to make it like that day or something, but I've used it several months old and it still works, but maybe it would work better if it were fresher. But yeah, so that's the basics. I line up my plates and then I squirt some 70% ethanol, and then I come and I clean them, and it makes nice squeaky noises. And so I do that for all of these, and then I'm letting them air dry. So I like to line them up like this, so then what I do is I can just flip directly over and stick it in the tray. And so make sure you put the sides that you, this way where you flip it, make sure, so you're making sure you put the sides that you clean together. Okay, I've got everything ready. I have everything I need right nearby, and it is go time. So I normally do it in like a 50 ml Falcon, but because I'm making a lot, I'm doing it in one of these tubes. So this is for like a 0.75 mil gel. So since I have a 1.5, I'll be doubling that per gel, and then I always make like enough for one extra in case one's leaking. I can fix it and then fill it up. And so I'm going to add the APS and the TMAD, and that's going to start the polymerization that I'll tell you about. And then it's go time, and so after I add, I shake a little gently so you don't get bubbles. The other, shake a little, or rock a little so you don't get bubbles, and then I'm going to pipette in the liquid up to about the line, leaving room for the stacking gel because this is the running or resolving mix. So I've got a 10% APS solution. Gently rocking as I go over to the hood, gently rocking as I walk back from the hood. So now the polymerization process has started, and so should my pipetting. Going from the top corner. See it feel nice. I don't know if you can see that in the video. Just go to about there. It's a little rough on the edges, but I will even that out with the isopropanol layer I add after. So I think they're all okay. This one looks like it might be leaking. I'm not sure, but I spilled when I was making it. So I'm not sure, but now it's time to put the isopropanol layer on top so that to even out the top, create a nice layer, a nice line so you don't have all wiggly. And then it'll also help prevent it from drying out. Before we add the stacking gel, we'll pour this off and rinse the top with water. I always make more than I think that I'm gonna need, so I need 5 this morning, so I'm making 8 just in case I need to like redo the experiment or anything. And also in case some leak, because that one does look like it. I think that one back there is leaking. But I have extras. So now it is going to let this set, and I'll know when it's ready because I keep the pipette in the little excess fluid, and so when this liquid polymerizes, then this pipette should get stuck in there, and then I can wave it around and stuff, which is fun. Okay, so now you can see that this is like stuck, or I mean it's hardened. It's pretty cool. You can take it out, you can see a thing. Okay, but anyway, so that means that it's time to do the stacking. So first I need to pour off the isopropanol, so I'm gonna just like tilt it and pour it into the sink, and then use this this nice double distilled water, so like Milky water. I'll run it over, pour it out, do a couple rinses with the water to make sure everything gets off. So now I've rinsed them off, and I'm just gonna help get the excess liquid out. Just like a little Kim wipe in the corner, because I don't want the water to be there when we are going to add the stacking mix. And then I'm going to get my combs ready, so that I will have the combs ready to put in as soon as I add the stacking gel. So once again, I have everything ready to go before I get the polymerization going. And this time it includes combs. So I'm making 10 mil, so I'm doing 10 mil combs. Make sure your comb matches the thickness of your gel. So I've gotten the polymerization going. Now I'm gonna put on the stacking gel. So just like before, except here I fill it up all the way to the top. So I typically prepare like 3.5 mils for a 0.75 gel, like 7 mils for a normal gel of the running, and then 2 mils of the stacking. And then you just insert your comb, so start from the corner, just go down. So I'm just gonna spill over. A thing to note about this is that polyacrylamide is toxic before it polymerizes. So you want to be careful and wear gloves and clean up well and that sort of thing. You want to avoid there being anything like stuck or any bubbles or anything in between the wells. That'll warp things. So you want to do this quickly so that it doesn't have time to polymerize it all before it's done. Okay, so now this is going to set, and going to go change my gloves and clean up. The stacking gel has set, so the gels are done. They've actually been done for a while. I already took 4 and started those gels running, and now I'm going to wrap up the rest for use later. I'll run the 5th layer this morning, and hopefully I won't need to run the other ones, but it's nice to have backup. So what we're going to need to do is, when you store them, you want to keep them from drying out. So I wrap them in wet paper towels and then saran wrap. But first you need to take like the cassettes off and stuff. So when you take it off, there's going to be like gooey stuff. So do it on like a paper towel. And then what I do is I just like wipe off the excess gunk. And then you just do that for all of them. So now I have my gels, and I am going to take some trifold paper towels are really great for this, and I'm going to get these wet, and then I'm going to wrap it around them and start them. So I do like stacks of 2, so that you don't have to unwrap them too much, so you don't have to unwrap them and then potentially have the rest dry out. So I just fold and flip and flip. So this is the trifold ones seem to be a nice height for this. Okay, so now I just need to wrap up the stacks. And I'm just gonna label them. So I label them with the percentage and so new page, that's just like the type of gel it is. Like there's also like tricine, trisglycine, there's a bunch of different types. But this is the new page formula. Then the thickness and number of wells, date, and my initials. And now it is off to the fridge. So these can actually last for quite some time. The bigger problem is that you can get mold growing on the paper towels, which is gross. So I label them with the percentage and so new page, that's just like the type of gel it is. Like there's also like tricine, trisglycine, there's a bunch of different types. But this is the new page formula. Then the thickness and number of wells, date, and my initials. And now it is off to the fridge. So these can actually last for quite some time. The bigger problem is that you can get mold growing on the paper towels, which is gross. Time to actually use one. So you can see that there is the stacking gel and then the resolving or running gel. And when I pull out the combs, now you can see that there are wells there that I'm going to stick my protein in, and if you want to know more about running SDS pages, I have more other posts on that. So yeah, in case anyone doubted that I was being serious about the 750 SDS page gels, yeah, I've gone through a lot, and I've casted a lot at the same time. So what's actually happening when we're doing this casting? So the key players that we have are this acrylamide bisque solution, ammonium persulfate, and TEMED or TEMD, NNNN tetramethyldiamine. Yeah, I usually call it TMED, but I don't know how people normally pronounce it. And then you have these gel plates, and your combs and the casters and stuff. And so the basic idea is to take this solution and get it to polymerize. And so we're going to dilute this solution to various amounts, depending on how thick of a mesh that we want. And so we dilute it in like a buffer, so a pH stabilizer. So we have a consistent pH and everything's all cool. And then, but we're going to change the amount of the, like the meshiness. So, and in order to get any sort of meshiness, we need to use these APS and this TMED to get this oxidation radical reaction going. So the basic idea, so what is a radical reaction? So going back to the idea of atoms being, so like individual carbons, hydrogens, nitrogens, all of that goodies. They're made up of individual units called atoms. And so these atoms have subatomic particles. There's the nucleus where you have positively charged protons and neutral neutrons. And then around that, you have this cloud of negatively charged electrons. And so the electrons is where the cool stuff happens usually. And so these electrons, so atoms can share pairs of electrons in order to form bonds. And so you can share a single pair to form a single bond, or two pairs to form a double bond. Electrons can also be as unbonded lone pairs. So like oxygen, it has these lone pairs. And so that's all normal. What's pretty unusual is a radical. And why it's unusual is because it's super unstable. Because molecules really hate having lone electrons. And so they can undergo radical chain reactions. And so that's what we're going to see. The other terms that we need to know are oxidation and reduction. So you can remember the mnemonic oil rig. Oxidation is loss of electrons, and reduction is gain of electrons. So one molecule gains electrons, and we say that it's been reduced. Another loses electrons, and we say that it's been oxidized. We can also represent the flow of electrons between molecules. So electrons can share and take and give electrons in order to get like the configuration that they want. So typically like having like a full valence shell or whatever, but regardless of whatever, they really don't want that radical. So we're going to see this chain reaction. And when we see the movement of a single electron, we draw that as like a one-headed arrow or like this push hook. And two electrons is this double-headed arrow. And so we're going to see some arrows in a minute. So with a radical chain reaction, what you have, it's like a game of electron hot potato. And so you have an initiation step where you need to create the radical. So you take something that's not radical and make it radical. And remember, radical just means it has a lone electron. It's unpaired. And then you enter the propagation phase. And so this is where a radical makes something else radical. And so the radical can then attack something, and then it can, then you have it can combine to make this bigger radical thing. Sometimes you can also have it where one thing, then this thing will be just take from another thing, and then that thing will become a radical, but they don't actually join. So there's different things that can happen. But what we're talking about with radical polymerization, here you have it like joining on, but staying with that other molecule. So then you have this bigger radical. And you can keep this going to get more and more things attached. So by polymerization, so a polymer is just something with a bunch of repeating units. And so we actually have like natural biological polymers are like DNA and RNA and protein. And so those are chains of nucleic acids or amino acids. And so those aren't all identical. They don't have, the units don't have to be identical, but they're similar units. And so they have the same sort of backbone, and they're connecting up. So in this case, we're connecting acrylamide. So our thing would be acrylamide. And so occasionally what can happen is termination, where two radicals come together and now they have a pair, and so they're happy and they stop attacking things. But as long as you have a radical, it's going to keep attacking things because it wants to get a second electron. And so you can take an acrylamide, and as we'll see, we can make an acrylamide radical. And once you have an acrylamide radical, then it can attack another acrylamide that's non-radical. So this is an acrylamide monomer. So a monomer, there's only a single one. A polymer, there's like more in a chain. And so then this can attack, and then you can keep getting this like path, like I don't want this electron, and so it attacks something to get another electron. And you can see here we have these like fishhook arrows because we have a single electron moving, but it's moving from one to the other, and then you're getting this long linear polyacrylamide. But a polyacrylamide, like just like a linear one, wouldn't be a very good gel, would it? You just have these strands, and we need to make a mesh. In order to make a mesh, we need to branch between the chains. But with acrylamide, you only have like a single point that you can like build from. With bisacrylamide, you can get cross links. So you have like these two sites that can be attacked. And since you have these two sites that can be attacked, it's like bifunctional. You can get these cross links between them, and you can get this branching. And so you can actually vary the amount of the various agents. So this is the bis, the NN-methylene bisacrylamide. So this is just abbreviated bis on those bottles. And you can see that there's various percentages of bis to acrylamide. And so since the acrylamide just has this one linkage point, you get straight chains, and then you can vary the amounts of this to get the chains. And so we can talk about different values, which is like, you can vary the amount of total monomer, and we call that's a T, and the ratio of the two types, which is C, as we'll see in a minute. And this will control how meshy the SDS PAGE gel is going to be. So if you have, this is just a chart from migration chart from Biorad's website. But basically it's just showing, so this is a 7.5% gel, a 10%, 12%. They also have gradient gels, so like 4 to 15, 4 to 20. And you can see that, so for a lower concentration, a lower percentage gel, the bigger proteins, so this is like it's going to be better for separating these bigger proteins. So if you look at like a 12% gel, the 250 and the 150 kilodaltons, that's like a measure of molecular weight. So these are pretty squished together, and you want to be able to tell them apart very well. Whereas in the 7.5%, you have a better separation of those, but you don't even see the little gel, like the 25 to 15 or whatever, it's already run off the gel at this point. So you don't see those. And so this is good for separating big things, whereas this is good for separating little things. Then you can see that when you have these gradient gels, you can kind of get a better separation of everything, like a separation of everything, but not necessarily like as good of a separation as you would get if you had a gel that was, the percentage was centered around what you wanted it to be, and like what was right for the protein that you're interested in. But these are really good if you're trying to separate proteins, like you have a big protein and a little protein you want to see, or if you just want to see what's there kind of, and you're not worrying as much about whether a particular protein you're trying to purify is really pure. So in that case, you want to kind of see, like, are those two bands or is that just one band? And so we call that like resolution, being able to tell bands apart. In order to get all that happening, you need to have, to get that chain reaction going. So we need to make that radical. We need to make that acrylamide radical. And so like the way that we can do this is we use APS and TMAD. So remember the APS, we make like a solution of it. And keep it in the fridge, and then the TMAD, we keep it in the hood, and that's the smelly one. It smells really like sulfury. It's like fish eggy. So first we need to make that radical. So remember, anything radical can start the chain reaction going, but first you need to get that radical thing. And so we're going to get this radical things from APS, ammonium persulfate, and TMAD. And so ammonium persulfate, so it's this persulfate part that's going to be important. This ammonium is just like a counter ion. So a salt is a neutral combo of a cation, so a positively charged thing, and an anion, or negatively charged thing. And so you need like a counter ion to make the salt. So this is the salt form, but then when you dissolve it, these come apart. But anyway, it's this persulfate part that's important. And so basically it can split into radical sulfate ions if you heat it up, but that's not what we're going to do. Instead, we're going to get radicals from a redox reaction. And so in this reaction, we're going to have TMAD is actually its electrons are going to attack APS. This is going to cause it to lose a sulfate ion. And this makes this thing really uncomfy. Yeah. And so what's going to happen is you actually get this like rearrangement and this movement of these single electrons. So that's what this these fishhook arrows showing the single electrons. And so when those single electrons move, this sulfate atom is going to actually leave as a radical. So it has a lone electron, and it also leaves this electron behind on this TMAD. So you get these radicals, and now you have these radicals. They can go initiate those chain reactions to make the gel. Going back to like how meshy your gel will be, we actually have like terms that we define. So we can have this like %T is like the total amount of monomer. So it's the grams of acrylamide, crust plus linker divided by the volume times 100. So the reason why it's like grams and mils and 100 over, it's just the weight volume %.
So it's comparing the totals of the T monomer amounts to the amount of liquid. And then the percent C is like, if it were to run into a monomer, how likely is it that that monomer is a brancher, so the one of the vis, and it, as opposed to just one of the normal acrylamides. And so this is going to be your grams crosslinker divided by your grams acrylamide plus grams crosslinker. And so like, what percentage of the acrylamide is actually the crosslinker one? So this is a weight percentage comparing crosslinkers to all monomers, so that's why it's a C. And so you can buy different amount, like different percent Cs. And then you can make different amounts of Ts from any of those. And so typically what you see, like when you see like an 8% gel or whatever, this is talking about the total T. But when you're making your own and stuff, you can use different percentage of Cs. And I don't know what the different percentage of, what the different C percentages are for like pre-bought ones. I'm sure you can like find that information, hopefully. Yeah, and so then the idea, so we have this, we use a different percent in the stacking and the resolving gel. So I think the stacking gel is like 4%, but I don't want to say off the top of my head because I don't want to get it wrong. But basically, I don't know if you can see in this picture, but so like to here, you can see there's this line across here. So this part is the resolving or the running gel, and then this part is the stacking gel. And the basic idea with that, going back to, is that it's going to allow them to kind of like pile up before they run through.